Acid-base extraction, background. In this webcast, we will discuss what an acid-base extraction is and how it works. An extraction is a purification technique that separates solids and/or liquids via partitioning between two phases based on solute solubility. If you have ever made coffee or tea, you have performed an extraction. In coffee beans and tea leaves are numerous goodies, such as caffeine. In the case of coffee, you add hot water to ground coffee beans. You now have two phases, the solid coffee beans and the liquid water. The caffeine and other desirable compounds in the ground coffee beans move from the solid coffee beans into the liquid water. They partition themselves, and in doing so, separate themselves from everything else. In organic chemistry, we typically use what are called liquid-liquid extractions. A liquid-liquid extraction is an extraction that uses two immiscible solvents. We will talk about what immiscible means on the next slide. Usually, one of these solvents is aqueous, or made of water, and the other solvent is organic. The word immiscible here is quite important. Miscible and immiscible describe the ability of two liquids to mix with each other. Miscible liquids are liquids that will mix together in all ratios. An example of two miscible liquids is water and ethanol. Here on the slide, you see a bottle of vodka, which contains water and ethanol. This mixture appears to be homogeneous. We don't see any separations or barriers within this bottle. In contrast, an immiscible mixture is when you have two liquids that will not mix, will separate. Sometimes it depends on what ratio of liquids you are using. An example of this would be this balsamic vinaigrette. In balsamic vinaigrette, you have water and you have oil. If you take a bottle of balsamic vinaigrette and leave it sitting on the table for a while, you will see the two liquids separate and form layers. Here is a visual demonstration of an extraction that will show why using immiscible solvents is required. Here I have two compounds, yellow triangles and red squares, and let's put those compounds into this container. I'm now going to add some kind of solvent. Let's say an organic solvent of some kind. This solvent will dissolve my compounds. What I will add next is an aqueous layer, a layer made of water. And what will happen as a result of this is some of my compounds will prefer the aqueous layer over my organic layer. And as a result, they will move to the aqueous layer. In this case, my red squares favor the aqueous layer. The only reason this works is because these two liquids don't mix. If the two liquids mixed, you would have a single layer and there would be no way to separate the compounds. One note before I continue. You will notice that not all of my red squares have entered the aqueous layer. That is because compounds will always have some solubility in both solvents. What determines which layer a compound favors is that compound's polarity in comparison to the polarity of the solvents. The general golden rule for an extraction is like dissolves like. We know that water is a polar solvent. Based on the golden rule that we just discussed, that means that polar compounds will prefer to dissolve in water. The reason for this, as you can see here in this diagram, polar compounds have partial charges. We know that in water, all of our oxygens are delta negative and all of our hydrogens are delta positive. By dissolving polar compounds, such as ions, we can arrange the charges in a favorable manner that is energetically stable. As you can see here on the left, the positive ion is surrounded by partially negative oxygens, whereas the ion on the right, which is negative, is surrounded by partially positive hydrogen atoms. In contrast, organic solvents, which range from nonpolar to moderately polar, tend to dissolve neutral, non-charged compounds up to moderately polar compounds. Most organic compounds fall in this category of neutral to moderately polar. If most organic compounds have roughly the same polarity, then they should have roughly the same solubility. If they have roughly the same solubility, how can we separate them via an extraction? Remember, an extraction separates compounds because compounds will prefer to dissolve in one solvent over another. What we can do is we can exploit certain functional groups that may be present on certain compounds to change their polarity. In an acid-base extraction, we will use acids and bases to react with functional groups on molecules to change the polarity of those molecules. Before we continue, some fundamentals. The process of moving between layers in an extraction is an equilibrium, which we can represent via these equilibrium arrows here, where X sub AQ is the amount of compound in the aqueous layer, and X sub org is the amount of compound in the organic layer. And this K is what we call the partitioning coefficient. K is a ratio of the amount in the organic layer over the amount in the aqueous layer. If our compound prefers the organic layer, in other words, there is more compound in the organic layer, then the numerator is larger than the denominator, so K is greater than 1. In contrast, if our compound dissolves more in the aqueous layer than the organic layer, then the denominator is larger than the numerator, and so K is less than 1. As mentioned previously, most organic compounds are nonpolar to moderately polar. As a result, they will prefer the organic layer, and so they will have K values greater than 1. In contrast, salts are very polar and thus prefer the aqueous layer, and so their K values will be less than 1. Here is a visual demonstration of how we can use acid-base chemistry to separate compounds. In this example, the red squares represent a carboxylic acid, and the yellow triangles represent this ketone. I'm going to go ahead and, like before, place them into my container. I will then add an organic solvent of some kind, and this organic solvent will dissolve my mixture. Now I will, like before, add my water layer. But there's an issue. Both the red squares and the yellow triangles are organic compounds. They don't really like to dissolve in water. So, just by adding water, I get no separation. What if, instead of adding pure water, I instead add basic water? The base in my water will react with the carboxylic acid in the organic layer, turning my carboxylic acid into a salt, which you can see here now represented by the orange circles. And you know that salts are very polar, and that salts prefer the aqueous layer. If salts prefer the aqueous layer, they should partition themselves and move into the aqueous layer. Thus, we have successfully separated one of our compounds from the other. To recap, we had a mixture of a carboxylic acid and a ketone. Both of these are organic compounds that will not dissolve in pure water. Their polarities are too different from water. However, by adding basic water, we cause an acid-base reaction to occur, where our carboxylic acid is turned into a salt. This salt is very polar and thus moves into the polar aqueous layer. One note before we continue. Water is still the solvent. There is base dissolved in the water. This is why we call it a basic solution, but nothing is dissolving in base. In the examples you've seen so far, I have drawn the organic layer as being the bottom layer and the aqueous layer as being the top layer. Will this always be true? The answer is no. What determines which layer is the top layer and which layer is the bottom layer is the density of the layers. Liquids with higher densities will be the bottom layer. They will sink to the bottom. In contrast, liquids with lower densities will float to the top. Sometimes the aqueous layer will be the top layer, and sometimes the aqueous layer will be the bottom layer. It depends on the density of the organic solvent you use. If you don't know which layer is which, how can you identify them? You can perform a water drop test. By adding a drop of water to the top of your mixture, the water will encounter this top layer. If this top layer is aqueous, your drop will simply disappear because water will mix with water. If your top layer is organic, your water droplet will pass through the top layer and reach the bottom layer. Let's say I tell you which solvents you are using, but I don't give you their density values. Is there a quick way for you to tell which layer is the top and which layer is the bottom? There is a rule of thumb you can use. Chlorinated solvents, such as methylene chloride and chloroform, are dense. As a result, chlorinated solvents tend to be the bottom layer in an acid-base extraction. In contrast, most other organic solvents tend to be the top layer in an extraction because they are less dense than water. So remember that rule of thumb. Chlorinated solvents, more dense, bottom layer. Everything else, less dense, top layer. That brings us to the end of this webcast. To recap, extraction is a method to purify mixtures of compounds. Compounds are separated after changing the polarity of compounds within that mixture. In the case of an acid-base extraction, we use acid-base chemistry to perform a chemical reaction that converts compounds from their neutral state into very polar salts. Compounds prefer to dissolve in the solvent that is most similar to their polarity. Very polar compounds, such as the salts we just described, prefer very polar such as aqueous solvents. Nonpolar to moderately polar compounds, most neutral organic compounds, prefer organic solvents. It is this difference in solvent preference that we exploit to separate compounds in a mixture in an acid-base extraction.